My name is Stan Szymanowicz, and it is my pleasure to present our paper Viewset Diffusion. This work was done at the VGG group at the University of Oxford with Christian Ruprecht and Andrea Vidaldi. Viewset diffusion is a method for generative few-view object 3D reconstruction. Given an input of n-conditioning images, Viewset diffusion generates plausible 3D volumes that match the conditioning images. For example, if we input one conditioning image, Viewset diffusion will be performing single-view 3D reconstruction. Viewset diffusion can also perform two-view 3D reconstruction or unconditional generation, depending on the number of input images. Viewset diffusion is trained from 2D data only and performs generation in a feed-forward manner without any distillation or optimization at test time. The key problem that Viewset diffusion addresses is the inherent ambiguity in 3D reconstruction, where the scale, shape, and occluded parts of objects are ambiguous given the single conditioning image. Under the presence of this ambiguity, regressive methods have to blur between the possible solutions, and they output blurry reconstructions which do not represent plausible shapes. Using an image conditioned generative model allows us to resolve this issue by capturing the ambiguity. We choose to use diffusion models due to their stable training and good conditioning properties. However, an extension of diffusion models in their original formulation to 3D requires 3D ground truth data, which significantly limits the applicability of these methods. Our goal is to train a model that can generate 3D objects without using 3D ground truth at training time. The key idea to achieve that is to generate view sets, which we define as 3D consistent multi-view image sets. We achieve 3D consistency by defining the denoising function as a composition of reconstruction and rendering. We implement this denoising function with a multi-view reconstructor, which takes a set of images as an input and outputs a 3D volume. We then render the volume from the camera viewpoints of the input images. Because the whole pipeline is end-to-end differentiable, we can train the network with just the rendering losses and without any supervision of the 3D volume. However, at every step of the denoising process, we output 3D volumes, thus generating those too. At inference, we start with a set of Gaussian noise samples and jointly denoise them, allowing the model to perform unconditional 3D generation. We can extend the method to 3D reconstruction naturally by simply including the conditioning image in the input viewset at every step of the denoising process. By sampling different Gaussian noises at every step of the diffusion process, Viewset diffusion is able to output multiple samples of 3D shapes that match the conditioning image. Due to using a generative approach, our model can elegantly capture ambiguities in single-view 3D reconstruction. Where regressive methods blur between the possible solutions, our method can sample sharp reconstructions. Viewset diffusion outputs high-quality reconstructions of ShapeNet cars, Go3D hydrants, and Minance characters from a dataset we introduce in this work. Compared to prior work, Viewset diffusion outputs sharper and more plausible 3D shapes. The same models can perform unconditional 3D generation without any further training or fine-tuning by simply changing the nature of the input to the model. We compare performance of Viewset diffusion to render diffusion. Render diffusion performs 3D generation by progressively denoising and reconstructing 3D volumes from a single image. We improve on the generation performance by using the architecture from Viewset diffusion, but the best quality is achieved with Viewset diffusion, because a set of images can describe the full 360 degrees of an object. Viewset diffusion can unconditionally generate high-quality 3D object samples. Thank you for listening.